Good morning, everybody. We'll get started in a minute or two. So if you want to grab a quick coffee or cup of tea, you have got time. We'll just wait for a few more people to join and then we'll get started. Okay, I think we're probably just about ready. So good morning, everyone. Thank you for joining us today. We're AcSoft. We're based in Bedford in the UK, and we are the UK representatives of Microflone. Today, we've got Jared from Microflone discussing all things in situ acoustic testing with us. This webinar will probably last about half an hour or so. And what we'll do is we'll send you an email afterwards with a replay link for you as well, in case you just wanted to refer back to anything. If you have any questions or comments, there is a chat box. But if we miss anything, then please do email us on sales@acsoft.co.uk and we will come back to you. We're very lucky to have Jared with us on the week commencing the 15th of June to do demos of his Scan and Paint 3D kit. At the moment, we've got a couple of slots free still. So if anybody is of interest in that, then please do let us know and we'll see if we can get you booked in. And I think that's everything for now. So thank you again for joining. And Jared, over to you.
All right. Thank you very much, Paige. I hope you guys are having some better weather than I am here in the Netherlands right now. It's quite stormy. I don't know there where you're at in the UK.
Yeah, it's not very nice out there.
Yeah. Well, but first I'd like to thank you, Paige, for the introduction, and also to AcSoft for organizing today's webinar. You guys have done a great job on setting everything up. And to all of our participants, thank you very much for joining. I'm excited to guide you through today's session. I believe it'll be quite useful for you. We're really going to discuss in situ acoustic testing using the Microflone products. So without further ado, let's go ahead and get started on the webinar. All right, so Microflone Technologies, for those of you who do not know, has been a pioneer in the field of acoustic testing since 1998. After inventing the world's very first acoustic particle velocity sensor. Since then, the company has transformed the world of acoustic testing by providing a wide range of particle velocity-based sensors and complete measurement solutions. Our high-quality products have earned the trust of customers worldwide for over 25 years now. So we've been around for a bit. Our technology enables advanced analysis and visualization of sound fields with high spatial resolution for 2D and 3D, and enables precise source localization, quantification, as well as ranking. With over 700 publications, we have research-backed solutions for acoustics, material testing, as well as end-of-line testing. And this is possible over a broadband frequency range, and even in the most challenging of acoustic environments, which we're focusing on a little bit more today, thanks to the unique properties of the particle velocity sensor. But before we begin, let's discuss some of the challenges that us as acousticians, as engineers face when we're trying to perform measurements in in situ environments. These are quite unique challenges that can significantly impact the quality and reliability of the data that we measure. So let's go ahead and discuss these. The first is environmental conditions. Unlike in controlled laboratory settings, such as like an anechoic chamber or reverberation room, where we really know what to expect, In situ environments are subject to varying weather conditions, such as wind, temperature, fluctuations, and humidity. And these factors can affect both the propagation of sound and the performance of measurement equipment. And this can lead to variability in our results. In situ environments are often noisy, with multiple sources of background noise that can interfere with the measurements of the target source. For example, say we're measuring an aircraft engine on a tarmac. Aircraft noise from normal operations, or say environmental noise from birds, or traffic noise can often impact the measurements that we are conducting there in the field. And we also have issues with acoustic reflections. These can cause measurement distortions and complicate source identification. This is most significant in environments where sound can bounce off reflective sources or nearby objects. So those can be broken down here into two categories. First is measurement distortions, where reflections can lead to distortions in the measured sound levels as they cause constructive and destructive interference with direct sound source or sound from the noise source. This interference can create areas of either high or low sound pressure, depending on the phase relationship between the direct and reflective waves. Also, we have to deal with echoes and reverberation. So in large or enclosed spaces, sound can reflect multiple times, leading to echoes and reverberation. This can extend the duration of the sound and complicate the measurement process. Reverberation can obscure the true characteristics of the noise source, making it difficult to identify specific noise contributors. And this is really the case, I know, if we've all experienced this, say, in a factory setting with a reflective environment, you hear that reverberation time much longer than you do in, say, an absorptive room. In situ testing often involves working in confined or difficult to access spaces, such as inside aircraft fuselages or under the hood of a vehicle. These constraints can limit the placement and movement of sensors, making it challenging to capture all relevant noise sources accurately. So say you're under the hood of a car, you need to measure all around this complex device. We really have difficulties sometimes being able to accurately measure the acoustic field in these confined spaces. So often sources in these fields are also very complex, containing many components and interactions that contribute to the overall noise level and behavior of the acoustic field. So often complex machinery or vehicles cannot be broken down or simplified as a superposition of a few monopoles, as we sometimes like to do in acoustics. And furthermore, if there is significant low frequency excitation, there is additional difficulty in added due to the associated large wavelengths and the strong interactions with the surroundings. So that low frequency behavior also becomes difficult to characterize with complex acoustic sources. And finally, difficult equipment setups. Engineering grade acoustic measurement equipment can be difficult to deploy in the field, requiring power banks, extensive cabling, and large data acquisition devices. So measurement campaigns can often require weeks of planning or hours of equipment setup. So these are some of the challenges that acoustic engineers face in the field when trying to perform accurate acoustic measurements. So how can we get around some of these challenges? Well, let's first talk about the advantages of particle velocity. There are several fundamental differences between sound pressure and particle velocity. So if we look at this diagram to the left here, we see that we get a near field boost with particle velocity. So when we're close to a vibrating surface in the near field, the particle velocity amplitude is significantly higher than that of sound pressure. And this occurs because particle velocity can measure the surface vibration as well as the evanescent wave when we're close to the surface. So we get this near field boost when we are close to that vibrating surface. Second, we get a natural background noise reduction. So we see the opposite effect when we get near a rigid surface, so a surface that is not vibrating. Here, the particle velocity amplitude is lower than that of the sound pressure. And this occurs because the incident and reflective waves are in phase for sound pressure, leading to constructive interference, while they're out of phase for particle velocity, leading to destructive interference. So the combination of these two differences leads to a much higher signal-to-noise ratio for particle velocity when we're in the near field. And then finally, to the right here, we're looking at broadband directivity. So the directivity of a standard omnidirectional pressure mic can be seen here in blue, and particle velocity transducer in red. So the particle velocity sensor has a figure of 8 directivity due to particle velocity being a vector. So we get also a direction. This automatically reduces the sound energy collected by the sensor by a third, enabling a technician to obtain data only in the direction desired. And this allows particle velocity sensors to be used as a frequency-independent spatial filter, therefore reducing the impact of background noise just by being able to point the sensor at what we want to measure. So the combination of these three fundamental values of particle velocity leads to a higher signal-to-noise ratio, better accuracy when identifying noise sources, and a sensor that is less susceptible to background noise. And the three of these really make it ideal for in situ environments. So next, we're going to show a video that explains this phenomenon. So in this video, we have two speakers, one speaker here to the left and one to the right, placed orthogonal to each other. One will play white noise while the other will play a tune. So here we can see the difference between particle velocity as well as sound pressure when we rotate the transducer in the near field. So this shows how you can really define two different sources placed very close together in situ environments to really be able to locate your sources accurately using particle velocity. All right, now that we understand the benefits of particle velocity and how we can use it in our field measurements, let's take a look at a few practical applications as well as case studies to show really how this has been used in the past. So we'll start off with a case study using a microfilm Voyager. This is the product shown here. Get my laser out here in the bottom left of the image. This is, you can consider it a mobile tablet for acoustics usage. So we have a battery-powered device that we can take out in the field. We can attach our particle velocity, or this is a sound intensity, a 1D sound intensity probe to the device, and then we can really use it in the field for, say, source localization. So in this photo, the directivity of this probe is out of the tip of the sensor itself. So we are trying to characterize the noise from the HVAC system here in the cabin of this vehicle, and we immediately get a result here on the screen, a live result of the spectrum, looking at velocity as well as sound pressure. So looking about how that is used in the field, we first have an example of EV motor noise detection. So here we can see a photo on the left of a technician. He needs to identify a problematic high tonal excitation on the top of this EV motor. But this needs to be done in their testing facilities, a very small space with equipment in the background, reflective walls. So this is an area that has high background noise levels. So in this case, the technician is moving the microphone across the top of the source. And then here to the right, we can see the spectrum. So in blue, we see the sound pressure result as well as the particle velocity. And the tonal component of interest lies here a little bit above 1000 hertz. And one thing you might notice is how prominent the peak is with particle velocity. So you really have no doubt you see this high peak with the particle velocity sensor, while it's much smaller than that with the sound pressure. So the particle velocity sensor clearly locates the problematic tonal components in this case, with the signal noise ratio approximately 20 dBs higher than that of sound pressure. And finding a source can be even easier using one of the many advanced features of Voyager. A real-time frequency filter can be activated to remove unwanted frequencies. So here we are actively listening to the source itself, moving the probe along the surface of the source to locate where the problematic acoustic energy is propagating from. And here, in this case, we have selected a band stop filter, which will remove the frequencies around 825 hertz and only allow active listening of the remaining frequencies. But here, high, low pass, as well as band pass filters can also be utilized for any application. So this can be easily toggled on and off to be able to further locate sources in the field. In collaboration with Rolls-Royce, we conducted measurements of a sound field generated by a newly installed large turbo compressor within a highly reverberant environment. So you can see here, this is in a large space, very reflective surfaces, concrete walls, metal, or concrete floors, metal walls. And this task also presented significant challenges due to the very high ambient noise levels, in this case reaching 115 dB, which was very significantly over the expected operational noise levels of the turbo compressor. These high levels required dual hearing protection for anyone in the space and limited technician exposure to just 30 minutes. So given these constraints, a very efficient solution was critical. And previous attempts using certain sound pressure-based methods proved inadequate to be able to locate the source due to all of those reflections and high reverberation in the room. So the microfilm scan and paint 2D solution was used to its rapid setup time and efficient measurement process. So here we can see the equipment required to the left. We have a camera as well as a computer. And then in this case, we're using the Voyager device also as a mobile DAC, so a mobile data acquisition unit. And so Voyager can easily be switched from mobile listening and analysis to just plugging it into the computer to be used as data acquisition. And that is, of course, plugged into one of our 1D sound intensity probes. So the acoustic signal of the sound field are acquired by manually moving a PU probe across a measurement plane while filming the event with a camera. So in this case, we can see in the middle photo here, the camera was pointed at the source while a technician was moving the probe along the source with an extension rod. On top of the probe, we used a wind cap. It's a very bright red wind cap, which we used to track the position of the probe itself using a post-processing algorithm. The results are then combined with a background image of the measured environment to visualize the sound source over the compressor itself. So here we can see the measurement process, and to the right we can see the tracking path of the sensor itself once the measurement was complete. And here we see the color map results of this case study. Due to the size of the compressor, it was measured in sections, 3 different sections. So on the left, we see the discharge side, the center, the compressor front, and the right, the suction side. And the average scanning time for each of these sections was just around 10 minutes. So this was done quite rapidly. The noise distribution pinpoints one dominant source in the middle section of the suction pipe. So here to the photo to the right, we clearly see the dominant source of this device. And this was a strainer, which was designed to capture debris left inside the pipe during the installation process. But unfortunately, in this case, the strainer's resonance frequency was being activated during the operation of the turbo compressor, causing the entire pipe to vibrate and produce excessive noise. So after replacing this faulty strainer, the noise level in the room was decreased by over 10 dB. Next, we'll move to a case for building acoustics. So in this case study, we analyzed the transmission loss and acoustic leakage of a wall in an office building. The room under investigation features a combination of reflective and absorptive surfaces, including, say, some thin carpeting on the floor and standard drop ceiling panels. And then the walls in this office were composed of concrete, metal, and glass. So not so much acoustic materials placed around the office. So, the acoustic measurements in the room can be quite challenging due to pronounced resonances at certain frequencies, especially those low frequency room modes, which can amplify specific noise components and skew the overall acoustic measurements. So to combat these challenges, we use the microflone Scan and Paint 2D solution. To perform the measurements, an omnidirectional sound source was placed on the other side of the wall, and both surfaces of the wall were scanned using the 2D solution. So here in the photo to the left, we can see the measurement process where we set up the camera, and then we do a scanning technique over the near field of the wall itself. And in the center, the particle velocity distribution is displayed as a broadband color map, where we clearly highlight the dominant acoustic leakages located at the top and bottom edges of the doors here, as well as some acoustic leakage on the window. The door, large window, and closet were then ranked. So we can see that on the right, the broadband spectrum, with the window in green, the door in red, and the closet in blue. The window resonance is identified at 87 Hertz. We can really see that here. That is the dominant resonance frequency, and is the dominant source, overall source below 140 Hertz. The door is shown at 165 Hertz here in the middle, and is dominant across the remainder of the spectrum. And finally here, the closet is shown at 265 Hertz, which is the resonance of the cavity, the air cavity, when the closet is empty. So we can really identify and characterize not only the transmission loss and leakage points of the wall itself, but we characterize all the components adding up to the total value. Next, we will look at sound absorption testing in an in situ environment. The sample under test is a 12 millimeter fibrous layer with a very thin aluminum foil bounded to the surface. We see that that was placed here on the floor in the middle of a mid-sized room, a very reflective room. And here we can measure the absorption coefficient as well as impedance using our in situ absorption solution. This tool, you can kind of see I know it's quite small. I'm holding it there. It has a known source with a probe located at a known distance from that source. So from using that, we can calculate the impedance and absorption of a sample. And we can also, and those results we can see here on the spectrum, but we can also combine the Scan and Paint 2D with this to view color maps of sound absorption across the material, which are shown here to the right. But to go back to this material in general, when this material was tested in a large reverberant chamber using ISO 354, the material consistently showed excellent low frequency absorption around 300 Hertz. So we see that result here in blue, where we have this high peak around 300 Hertz in the reverberation chamber method. However, when smaller samples of the same material were tested in an impedance tube, the results were completely different, showing almost no absorption below 500 Hertz. And you can see that here in the orange markers. Quite different, even though these are two very standardized and accepted methods. So then we used our in situ absorption setup to test a large sample of the material, and the results aligned very closely with the reverberant chamber measurements. And our results can be shown here in yellow, which very identically measure the reverberation chamber, showing that large peak of acoustic absorption around the 300 Hertz. So what is going on? Well, the mapping revealed that the materials seem to produce a membrane-like effect, absorbing sound efficiently at low frequencies when the sample is large. And this effect disappears when the sample is too small. So at low frequencies, shown here at 300 Hertz, the highest absorption occurs away from the sample edges, suggesting the presence of modal or resonant effects. In contrast, at higher frequencies, here shown at 200 Hertz, the edges of the sample show higher absorption due to the exposed fibrous edge. And this is expected on this type of material. Now we focus on the acoustic characterization of a large compressor designed by a company called Lantra. The objective was to identify and mitigate key noise sources within the pre-production unit, which we see here to the left, aiming to enhance its overall acoustic performance. The compressor is a positive displacement machine which produces one discharge per revolution and results in low frequency noise. Additionally, testing needed to be completed in situ, and a small transducer was required to fit in between the complex components that were located here inside the acoustic enclosure. So here the microflow Scan and Paint 3D solution was used to accurately characterize the acoustic behavior of the entire system. So here we can see that solution, Scan and Paint 3D, very similar to the 2D, and it works in the same way, but instead of needing to track the location across a plane, we now need to track the location of the probe in a volume. So to do that, we use this 3D tracking sphere and an infrared stereo camera to track with 6 degrees of freedom with high precision, down to 3 millimeters precision, the location of the probe. And here we see a 3D sound intensity microfilm probe attached to the sphere. It does contain 4 channels, so particle velocity in the X, Y, and Z direction, as well as sound pressure, all located near the tip of the transducer, essentially at the same point in space. So with just this single probe, spatially dense and broadband frequency data was obtained, and this is accomplished by moving the probe around the surface while its position is being tracked in real time. And after all the captures were completed, the recorded signals are split into multiple segments and assigned to their corresponding locations using a spatial algorithm. Here we can see the 3D sound intensity data, where we have not only magnitude of the acoustic results, which is shown via the color map, but also their directionality shown by vector response, or by vectors. So here the sound pressure, particle velocity, or sound intensity across the field can be computed to provide this visual representation of the sound distribution. So this solution provided precise identification of noise sources within the enclosure, radiated from the complex device and from external emissions by scanning around the compressor itself. Through effective source ranking, the acoustic issues were prioritized and targeted, ensuring improvements with minimal modifications in cost. So here we can see some of the improvements that were made to the system that were discovered through scanning the interior components of the compressor, as well as some improvements that were made to the enclosure itself. So the improved enclosure was then scanned again, and the results were compared to quantify the improvement. To the left, we see the before and after sound power ranking of each side, and to the right, the before and after color map, where we see a significant reduction near the exhaust outlet. So the total A-weighted sound power emission from the enclosure was reduced by 3.3 dB, which was significantly helped by the 6.4 dB reduction in emission from the rear of the enclosure, which was here at the outlet pipe cover. So Scan and Paint 3D allows us to capture the full vector behavior of sound and how it propagates and interacts with different structures in a complex environment. This is especially useful for analyzing large enclosed volumes, or 3D cavities. So in this case, we use the system to visualize the sound field in an entire room. So the customer here, it was a company called Denoise, developed an active noise control system, which was mounted on a glass window. We see that window here to the photo to the left, where we had an actuator on here for active noise control. And this was designed to reduce external noise from say traffic or airports. So this case was close to the Amsterdam airport, where there was a test house. So the company wanted to understand how the sound generated by the vibrating window enters the room and how it propagates through the space. So we really need to characterize this space inside this room. So this was done by scanning a horizontal plane around chest height inside the room itself. So we can see the 3D A-weighted sound intensity results in a video This is spanning from low frequency to high frequency. So we see not only the magnitudes in these results, but also that acoustic characterization. So the results showed that at low frequency, the active sound intensity field exhibited strong modal behavior. Here we can see these vortices forming here in these low frequencies. And as we move to the higher frequencies, the sound field becomes more diffuse, and near the window, it begins to resemble a piston-like source radiating from a rigid baffle. So yeah, here we can see those pistons radiating from the window itself. So this example shows how 3D sound intensity visualizations can effectively characterize not only the source, but the entire sound field itself. And I think for our last example for today, because I realize we're already running out of time, we will examine how particle velocity can be used in aircraft cabin noise assessments. So the main goal of this investigation with Lufthansa was to evaluate the different panels and the acoustic behavior of the connections between them. So here to the left, you can see the first step that we use, not only in this case study, but typically in any type of measurement campaign. We get Voyager out to listen to the key locations, because normally we have a very large space. We're trying to really narrow down our acoustic sources. And we can do that by easily actually listening to particle velocity with Voyager and moving the probe around the source of interest. And then once we find our key areas, we can use more advanced solutions like the 2D or 3D solutions to fully visualize the acoustic fields in those areas to help us pinpoint the acoustic behavior and rapidly create design modifications for improvements. So after we did that step with Voyager, we performed a series of scan and paint 3D measurements, mapping the full sound field across key structural panels, here shown to the right. This allowed us to clearly identify leakage paths between different components, as well as resonance issues across multiple frequency bands. The system was successfully used to investigate this complex acoustic environment, this enclosure, and the insights gained were used to improve the aircraft's overall acoustic treatment package. So in conclusion, particle velocity probes are ideal for in situ measurements, thanks to those benefits that we get with particle velocity sensors. So using particle velocity sensors help us mitigate environmental noise and reflections when we're out in the field, and are very robust to varying environmental conditions. The compact size, they're all 1/2 inch form factor to achieve 3D sound intensity, makes it very portable and easy to deploy. We do offer a wide range of testing solutions for varying noise issues, any issues that you might face. And these solutions are very effective for noise source localization, as well as sound quantification and ranking. So with that, I will conclude the webinar. Thank you very much for attending today. I appreciate your time. I hope you found it insightful. And if you have any questions, I would be happy to answer them in email or after the presentation.
Lovely. Thank you very much, Jared. And thank you everyone for joining. Just a reminder, the email address for questions is sales@acsoft.co.uk. And the week that Jared is with us in the UK is the 15th of June. So just 2 slots left for that, for the Scan and Paint 3D kit. So let us know if you're interested. Thanks again.